Hello, my name is Alan Garner. I am the undergraduate program chair of nuclear engineering and a professor within nuclear engineering. And today I'm going to talk to you about opportunities within our major and what you can get out of our major by joining it. First, I will present an overview of what nuclear engineering is and what sort of opportunities there are within our school. So over this presentation, I will talk about why nuclear engineering, what the nuclear engineering program is like, student experiences, and extracurricular activities and student life. To start, I'm going to talk a little bit about my career first. I was an undergraduate nuclear engineer at one point. I got my degree from the University of Illinois. I was in the Naval Reserve ROTC program and ultimately received my commission in the Navy. In the Navy, as you can see here, this is what we call a career planner. I started off as an active duty submarine officer, went through Naval Nuclear Power School, submarine officer school for about a year and a half. I was stationed on board the USS Pasadena, where I was reactor controls assistant in charge of all the instrumentation and controls in the reactor plant, chemistry and radiological controls assistant in charge of managing personnel exposure and the water chemistry on board the submarine to make sure we didn't have corrosion. Quality assurance officer, which meant that I was in charge of keeping the submarine afloat and making sure that it came back to the surface after it submerged, and communications officer. So one of the things that you will see here is that my initial career was very, very much aligned with what students may typically think of as nuclear engineering. In other words, if I were to ask you what's the first thing that comes to mind in nuclear engineering, two things typically come to mind. One is the nuclear weapon, nuclear bomb, particularly those of you that recently watched the movie Oppenheimer. And the other thing are nuclear power plants, which provide around 20-25% of the electricity demand in the United States. So I started off my career in that sort of realm. However, that was not my full intention for majoring in nuclear engineering. One of the reasons I majored in nuclear engineering was that to understand how a reactor operates, to be able to understand the construction and the function of a reactor, you have to understand all of the bits and pieces. So when you major in nuclear engineering, or when you go to Naval Nuclear Power School like I did, you have to understand the basic materials. You have to understand basic electrical circuits, power generation, thermodynamics, heat transfer, fluid mechanics. One of the things that really appealed to me about a nuclear engineering major was that I had to understand the fundamentals and the basics of everyone else's degree so that I could understand how a reactor plant operated. By understanding all those fundamentals, I felt that that would make me a stronger engineer. And what it has allowed me to do is be able to successfully cross disciplines throughout my civilian and military careers. And increasingly, if you look at job postings or if you talk to people in industry, and I worked in industry for 6 years before joining Purdue University, one of the things that they will talk about is that the problems are increasingly multidisciplinary. And having a basic understanding of these basic areas will make you a stronger candidate as you move around your career. So before I joined the Navy with my commission after my undergraduate degree, one of the things that I worked on was a master's degree. I took a leave of absence from the Navy and actually went and pursued a master's degree in nuclear engineering from the University of Michigan. And what I studied was theoretical plasma physics. It was funded by the Navy, and it mainly focused on understanding the cause of noise in a type of high power amplifier called a cross-field amplifier. And that was a very important experience for me. It showed me that there was something other than the Navy. There were opportunities in research and development. So at the end of my sea duty on the USS Pasadena, I went to shore duty. I pursued a second master's degree in electrical engineering, where I took all of those plasma and nuclear engineering technologies that I'd learned from my master's degree, and I learned how they applied to the biomedical side. So I left active duty, became a reserve officer. I worked for a unit called ComSub Group 8 for a little less than 3 years. I finished my PhD at the University of Michigan, continuing the work that I'd done at Old Dominion University. And then I shifted over into industry. I worked for 6 years at GE Global Research. And again, the nuclear engineering background was very valuable there. I was able to work on problems related to healthcare, to life sciences, to Lockheed Martin, defense programs. I was able to work across disciplines, which is something that if I'd have majored in, say, electrical engineering, would have been much more difficult. In parallel, I continued my naval career, and I transitioned to become what's called an engineering duty officer. So as an engineering duty officer, I work for Naval Sea Systems Command, which is in charge of procuring and developing and maintaining the fleet of the United States Navy. So we do everything from constructing and maintaining submarines and surface ships to developing new weapon systems. And throughout my naval career, which continues from 2007 to present on the top of this graph, I've worked on various parts of this. I've worked with a group called SurgeMain that provides shipyard support through enlisted personnel. I've worked in NAVSEA Acquisition Unit, which I've worked on railgun modeling for Naval Research Lab and Naval Surface Warfare Center in Dahlgren. I've worked in directed energy, which uses a lot of the technologies I learned in graduate school, like high power electronics, high power microwaves. And I've also worked with the Office of Naval Research, which funds the basic research, including research that goes on here at Purdue University. And I developed white papers and wrote papers trying to characterize how we can take these basic plasma techniques and apply them to treating wounds for the warfighter. Since joining Purdue in 2012, I've set up a research group that studies these technologies. I have 10 graduate students and numerous undergraduate students that work with me in research in high power electromagnetism, biomedical applications of these technologies. We work with Department of Defense labs. We work with Sandia National Labs, which is part of the Department of Energy. And we've even worked with Syngenta, which is an agricultural company. So out of all these experiences, one of the things I want you to take away is that a nuclear engineering degree, while it does open up a lot of specialized opportunities in reactor power, nuclear weapons, which is another example we've used, radiation exposure, these sort of technologies that do require specific nuclear techniques, right? In addition to that, it gives you a fundamental background that gives you a lot of flexibility in your future career. So what is nuclear engineering? Well, we've talked a little bit about this already. So nuclear engineering is fission and fusion. Fission is what currently powers the electric production in the United States, right? 20 to 25%. Within the last couple of years, we've seen developments in fusion. Lawrence Livermore National Lab in late 2022 reported that they had achieved break even at the National Ignition Facility, which is one of the huge thresholds for trying to make fusion an effective and relevant power generation technique. Non-proliferation, as long as there have been nuclear weapons, right? This is one of the things that Oppenheimer brought up. There's been a concern about bad actors getting access to nuclear materials. So non-proliferation is a combination of technology and social science and policy to ensure that we prohibit those people from getting access to nuclear materials. A close relation to non-proliferation is nuclear forensics. Nuclear forensics uses techniques of nuclear engineering, nuclear chemistry, nuclear physics to be able to characterize nuclear materials in the event they should ever be used for attribution. Medical applications. Many of you may be familiar with things such as X-ray machines, right? That's one of the early applications of nuclear engineering. You have PET scans, you have MRIs. Those of you that have had relatives or, heaven forbid, had to have undergone cancer treatment, you may have had to have undergone radiation therapy. These are typical medical applications of nuclear technologies. Particle accelerators, another important application. Again, you can use this to generate radioisotopes. You can use this to generate X-rays. A lot of applications related to nuclear engineering. And then finally, propulsion. Coming from my background, you have submarines and aircraft carriers in the Navy. Increasingly, there is interest in transporting personnel to Mars or into space further on longer space missions. To do that effectively, you need to develop propulsion that can be rugged and reliable, and nuclear technologies, both fission and fusion, are being studied in those areas. So I talked a little bit about this when I was talking about my background, but to study nuclear engineering, you need to understand a little about a lot of things. Our curriculum has within it basic mechanical engineering courses. In fact, the first 2.5 to 3 years of our curriculum closely resembles a mechanical engineering degree. Our students have to take statics and dynamics. They have to understand the basics of mechanics, in other words, thermodynamics, electrical circuits, material science, both a lab course and a lecture course, fluid mechanics, heat transfer. Our students take a fluid mechanics and heat transfer laboratory. We also take 2 electronics labs, radiation instrumentation, in the sophomore and the senior year. And of course, wouldn't be complete without nuclear physics, both general and as relevant to neutron physics, which is important for understanding reactor operation. So again, first 2 years and most of the third year very similar, if not identical, to mechanical engineering. With the right technical electives, though, our students have 4 technical electives that can be taken from engineering or science classes. You can actually tailor your degree. When I was a student, I tailored it towards electrical engineering because I was interested in plasma physics and fusion, which has a lot of things related to electromagnetism and then, of course, power generation. So I took a lot of electrical engineering courses. Our curriculum also aligns well with material science, both for understanding the effects of fission on materials or fusion. So there are courses that one can take to make the degree look a little bit more like material science. So in other words, we have unique breadth and depth for gaining multidisciplinary knowledge that can be applied to traditional applications like nuclear reactors or to more cutting edge things like fusion reactors or plasma physics. So with this vast array of things our students will learn, what do nuclear engineers actually do? Well, half of our graduates go to industry. The other half pursue advanced degrees to perform research in laboratories and universities. Now, one thing that I'll point out here is that it is not necessarily mandatory that our students go to graduate school. Because of the unique breadth of our degree and the relative proximity of a lot of our courses to physics, a lot of our students are more geared towards going to graduate school to begin with. There are many good jobs in industry, either at public utilities, the reactor plants themselves, within government, say working in shipyards or in reactor development there, or within various contractors for jobs straight out of undergraduate. For our students that go into graduate school, either for masters or PhDs, they tend to work in more specialized areas, such as, say, core design. Some will go and work in national laboratories. Many will go to Department of Energy or what is called NNSA, National Nuclear Security Agency. Several of my students have gone and worked within the Department of Defense. So there's a lot of flexibility in what our students do after graduating. Now, the average starting salary for an undergraduate degree as of 2023 is a little under $80,000, about $75,000. Median salary is $122,000. So the remuneration is fairly solid and comparable to other engineering majors. But I would say that one of the things that drives students to go into nuclear engineering is not necessarily the salary, but also the chance to make a difference, the chance to be a part of the solution for generating the next generation of sustainable energy, or to work in the current part of sustainable energy, or also to go into the security side. So now I'll talk a little bit about what these jobs look like. So again, power generation, nuclear engineering, the largest application space within that is nuclear reactors. So you see the standard US power plant in the upper right. Purdue University is working with Duke Power to investigate the feasibility of a small modular reactor to power the load here at Purdue University. You see down in the lower right a small modular reactor building. The idea is a small modular reactor building may be around 1/10 the size of a standard power plant, but that would make them less expensive and make it easier to build them more in bulk. So you could build many of those rather than incur the large expense of building a single power plant. Power generation through fusion. You see on the left an image of the Lawrence Livermore National Lab National Ignition Facility, and they created nuclear fusion ignition on December 5th. So you see on the right, upper right, the present, and then the lower right and upper left, you see the future of power generation in nuclear engineering. In addition to this, we have naval nuclear power. So there will always be reactors built in the United States. Every year there's a new nuclear powered submarine being built. Right now the U.S. Navy is building the USS Columbia class, which is the next generation ballistic missile submarine. Upper left, you see a nuclear powered aircraft carrier. All of our aircraft carriers and all of our submarines are nuclear powered. Each aircraft carrier has within it 2 reactors. So there will always be opportunities on the civilian side for designing and maintaining the fleet of nuclear vessels. And there will always be opportunities for people interested in serving in uniform to serve as commissioned officers like I used to do, either through Naval ROTC or through what's called the NUPOC program, Nuclear Propulsion Officer Candidate Program, where you are a regular student during the semester and during your academic career, and then you are commissioned after going through officer candidate school after completing your degree. There are other opportunities within national security as well. My research is in directed energy. Directed energy broadly uses high power electromagnetic radiation. So things like high power microwaves, lasers. All right. You see in the upper left an example. This is no longer in service, but it shows an example of a Marine Corps vehicle that has within it a high power microwave source. The lower right, you see a surface ship that uses a high power laser for targeting, say, drones or other close-in weapon support applications. So again, opportunities here more from a research and development side. Medical applications. Bottom of the slide here, you see medical imaging, radiation therapy, applications on the medical side that are more traditional. On the upper part, you see the work that we do, taking intense electromagnetic radiation and applying it to something like platelet activation. All right. So a lot of techniques that are both larger scale or smaller scale and at different levels of readiness for development, depending on your interest. Food and agriculture. So radiation can be used to delay ripening of fruits and vegetables. It can be also used to sterilize food. Both ionizing radiation and non-ionizing radiation, such as plasmas. You can see at the bottom of the slide here work that I did with a faculty member in food science. What he did was he'd take something like the tomatoes you see here, put them within a bag that was filled with different gases, apply high voltage to form a plasma. The reactive species from that plasma would then inactivate the microorganisms or kill them. And you can see here the middle picture of the tomato, you see the complete removal of any sort of fungus or virus or anything. On the right, you can see the one that's undergoing spoilage. Then I mentioned before propulsion. So the main application, the main interest in propulsion from NASA and from Department of Defense is for increasing the capability for space transportation. So there's a lot of effort from NASA to try to have a manned mission to Mars. And if you look at different techniques for powering that, you have potential solutions of nuclear thermal rockets, radioisotope power, where you leverage the charged particles that form from radioactive decay to give a current, essentially giving you a battery. Power for extraterrestrial bases. Once you actually get the people there, you're going to need some sort of sustainable power to have oxygen and electricity for survival. And then, of course, you have ion engines. So there's a lot of potential technological development related to nuclear engineering as far as space propulsion. And then, of course, you have other applications. I'm not going to go through this full list, but essentially what they are is unique applications of radiation, plasmas, high power electromagnetism for different things that cannot be done easily using standard technologies. So what skills and courses do nuclear engineers take and need? Well, probably the most important thing that you've probably gleaned from this presentation is that nuclear engineering requires a lot of technical skills. Most important thing, and this is something my parents always emphasized to me, because we are a broad major, you have to have a basic fundamental understanding of physics, math, statics, and thermodynamics. So whatever you wind up doing after graduation, that fundamental skill set will be highly valuable. It'll make you a highly skilled engineer. And again, a lot of the background is very similar to mechanical engineering. The other thing too, when you start thinking about putting together a reactor system, be it a fission reactor or a fusion reactor, it's a very complicated system. And if you can understand how a nuclear reactor comes together, you clearly demonstrate your ability to understand complicated systems. And as I mentioned before, companies are increasingly looking for people to understand multidisciplinary problems as well as understanding systems. And project management. You have to understand how to work well as a team, because no one can understand all of these different areas and be experts in every single one. While everyone will understand the basics of each, some people will be stronger than the others, and you'll need to leverage teamwork to do that. And that's one of the benefits of nuclear engineering. We tend to be a small major, maybe 30 to 50 people in a class. It allows you to know all of your classmates, and typically you will work together on assignments to make your way through. So our program, we have 126 credits for graduation. Minor requires right now 12 credits. We don't have formal pathways, but we do have tracks unofficially. So one of the things that you want to do is talk to your advisor, talk to faculty, figure out what areas within nuclear engineering are interesting to you. Is it neutron physics, thermal hydraulics, radiation detection, materials, plasma physics, fusion, health physics? You can use your technical electives to become expert in the area of most interest to you. Because of our technical electives, it does provide flexibility for minors. Typical minors are physics, math, which can be done with one extra class. We are increasingly seeing people pursue political science and foreign languages as minors. And for our ROTC people, naval science or aerospace science are also fairly common minors. We also see double majors, management. I've seen some poli-sci. Sometimes people will pursue double majors in aero or mechanical engineering due to some of the synergies. But it's also very straightforward to complete a bachelor's degree in nuclear engineering and then shift to a master's degree in either aero or mechanical, or if you plan appropriately, vice versa, to get a bachelor's degree in aero and shift to nuclear engineering for graduate school. So some of the courses that our students take. Nuclear 305, which is one that I used to teach. It is our second radiation laboratory that our students take senior year. And probably the coolest thing about this is that we now have a recently updated nuclear reactor over the last several years. So we are the only Nuclear Regulatory Commission licensed reactor that has digital instrumentation and controls. So that makes our reactor probably one of the most modern ones in the fleet, even though it is only 10 kilowatts. But what it does is it provides a lot of opportunities for learning, so understanding the power dynamics as a student, as well as for research. There are several faculty trying to understand how to leverage this digital instrumentation and control and understanding the security of going to a more computerized system. Thermal hydraulics lab. Again, thermal hydraulics is a very fundamental part of reactor power operations, and we have a designated lab that our students take second semester sophomore year. And you work in a large lab room and you actually get to see the fluids and the heat transfer. And it's a very hands-on lab. You learn a lot about the courses that you have taken, the 2 lecture courses that lead into this, and it's a very valuable course. And then probably the capstone to the whole thing is our senior design that students take senior year. So the nice thing about our senior design program is it is specifically aligned with industry. So we have industry sponsors come, propose projects, and then get selected to work with our students. So the students get to work on projects that are very relevant to what they will do after graduating and going into the workforce. And the projects can range from anything from novel reactor design to regulatory safety to even novel power generation techniques. So internship and club opportunities. In addition to the coursework, there are a lot of opportunities to have experiential learning. So our students do participate in co-op. They participate in internships with national laboratories, both Department of Defense, Department of Energy, utility companies, Navy contractors, fuel manufacturers. A lot of opportunities in research. We've got very large laboratory groups out of our department. One thing, being a smaller department, students have more direct access to faculty and vice versa. So there are a lot of opportunities to work with faculty on research, particularly research for credit during the undergraduate curriculum. And then over the years, we've had various study abroad opportunities. These have been done, say, in the Maymester to count for 3 credits as technical electives. We've had students go to Ukraine to visit Chernobyl, to the Netherlands for data mining, and to Jordan for artificial intelligence. These sort of opportunities will vary from year to year based on faculty availability and events around the world. So I'll go quickly through some examples. So we've had students do co-ops with Dominion Energy, which is a nuclear utility. A lot of their work is focused on the areas such as nuclear core design, tracking performance of the reactors, testing new software, things of that nature. We've also had students work at BWXT, which is another nuclear manufacturing company. They do work both commercially and for the Navy. They manufacture Navy reactors, research reactors, medical isotopes. There's also been opportunities with the high flux isotope reactor out of Oak Ridge National Laboratory. Clubs and organizations. So I'm going to go through a big list here. One thing to take away from this list is we are multidisciplinary. So we have opportunities that are more traditionally nuclear, such as women in nuclear, women in engineering. American Nuclear Society, which often hosts events on campus. They host guest speakers, so that's a very interesting thing for anyone interested in nuclear engineering, not just for our majors. We have an organization, Minorities in Nuclear Engineering and Sciences. Fusion Awareness Organization, which fluctuates, but given the recent advancements in fusion, has become much more active. Then we have the more multidisciplinary areas, such as the Institute for Nuclear Materials Management, IEEE, Institute of Electrical and Electronics Engineers. It's the largest technical institute in the world, and within it has a Nuclear and Plasma Science Society, to which nuclear engineers such as my group belong. Then we have our nuclear engineering ambassadors. They're the ones that will meet with prospective students, tour visitors and guests. And finally, the American Physical Society. Again, a lot of what we do is highly dependent on physics. So for instance, my group and other groups that do plasma physics will go to APS. Some of the groups that do more things related to materials and nuclear physics will also participate in APS. So what is a class size? Again, typical class size around 30 to 50 students. We give you the advantage of having that small school feel within a large university. So it's kind of the best of both worlds. You get to know your fellow students, you get to know the graduate students who often are your teaching assistants, and you get to know the faculty. So it's a very tight-knit community, a lot of opportunities for growth and relationships, and I always feel like there are a lot of opportunities for undergraduate students to major in nuclear engineering and pursue areas in our field. So for any questions, our academic program office email is there. That will connect you to our student services representative who can answer your questions or direct you to appropriate faculty members or other staff who can help you. Thank you very much, and wish you all the best.